Hello students, today we look forward into the new concept in module 2 in digital signal processing, that is the filtering of long data sequence, and it is a continuation of the previous concept which we discussed about linear filtering using DFT or DFT for linear filtering. So in this class we have to understand filtering of long data sequence or long duration sequence. So here we need to understand what do we mean by the filtering of long duration sequence, right? So till now we have understood whenever you want to process the input data of the limited number of samples with a system having impulse response h of n, we always predict its output y of n as a linear convolution between x of n and h of n, and both input sequence as well as the system impulse response having the finite number of samples. But in the case where the input sequence consists of the large number of samples values, then it is very difficult to perform the linear convolution, as well as it is impractical to store all the samples of the long data sequence because it takes more memory. If the system is having the limited memory storage, then it is very difficult to perform or process the long data sequence, because if you see the system impulse response, it consists of very few number of samples, right? So the input sequence is very long and the system response consists of a few number of samples, then there is difficulty in performing the linear convolution, and also it takes more computational time, as well as there is a problem with the memory storage also. So in order to overcome these problems, the solution is the filtering of the long data input sequence. So here what we do is, instead of performing the convolution between the long data sequence with the system response having the finite number of samples, we divide the long data sequence into a smaller blocks, and each small blocks are processed using the system response h of n using linear convolution. And once you perform the linear convolution between each small blocks with system response, then you combine all the linearly convolved output sequences, right? You will get the resultant, the output, that is y of n, which is the output of LTI system. And what are the methods which are available to do this? Mainly we have got two types of methods. Using those we can perform the filtering of long data sequence, which are overlap save method and overlap add method. So for your kind information, in your VTU external exam, definitely you will get one example, one theoretical question either on overlap save method or overlap add method, and also you will get one numerical example from either of these methods. So if the theory concept is asked from overlap save method, then definitely you will get the numerical example on overlap add method, and vice versa, right? So today we'll discuss the first method, which is overlap save method. So using this overlap save method, how to perform the linear convolution between the long data sequence and the system response h of n. So first we'll discuss the procedure, how to perform, then later we'll move on to the numerical example, right? So here what we do is, you will be having the long data sequence x of n. So please concentrate. You will be having a long data sequence x of n, more number of samples are there in that, and the finite length impulse response h of n is there, right? So write down x of n and h of n, and length of h of n is considered as m. Determine the length of h of n, and it is denoted by what? Capital M. So capital M is nothing but the length of impulse response, which is the number of samples present in h of n. Next, you note down the given input sequence x of n, right? And assume the size of DFT is capital N. The size of DFT is what? Capital N. Understood? I am not talking about the size of x of n. I am assuming the size of my DFT is capital N. Understood? So now I have to divide the input sequence, the long input sequence x of n, into the block of the input sequence of the finite number of samples, very small number of samples. So what you have to do is, you have to divide the sequence x of n into a smaller blocks. Then questions comes, when I divide the long input sequence into a block of a smaller sequence, what should be the length of each block after dividing? So the length of each block should be capital L, and that capital L should be calculated as, there is a relation n is equal to, that is the size of DFT, n is equal to L plus m minus 1, right? So this L is the number of samples or the length of each sub block or block. M is the number of samples in the impulse response h of n, that is the length of h of n, and using this relation you can calculate L. So L is equal to what? N minus m plus 1. Please remember, L is equal to n minus m plus n, and this L is the number of samples in each block, right? So once you divide the long data sequence into a smaller blocks, each small block should consist of how many number of samples? L number of sample, that is n minus m plus 1, where n is the size of DFT and m is the length of the impulse response h of n, right? And after that, before you perform the convolution, either linear convolution or circular convolution, if you take the circular convolution, as we discussed, to perform the circular convolution, the length of both the sequence should be what? Same, right? So therefore, before you perform the circular convolution, you have to make the length of both the sequence x of n as well as h of n should be same, and for that you have to add L minus 1 number of zeros to h of n, right? So step 4 is very important. L minus 1 zeros to h of n, right? At the end of h of n, you have to add L minus 1 number of zeros, right? So next, so here you can, step 4 you can see here. Step 3 is about determining the length of each block, that is L n minus m plus 1, and after that you have to add L minus 1 zeros to h of n, right? So here, for example, h of n is 1, 2, 3. We have 3 samples, but the size of DFT is 5. Size of DFT is what? 5. So we have to make the length of h of n is also 5, right? So here already we have 3 samples. Next, to make 5, we have to add L minus 1 number of zeros to h of n, and this L is nothing but what? It is the length of a small block after dividing x of n, right? Let's say x of n is the original long data sequence. After dividing, you will get the number of blocks, namely x1 of n, x2 of n, x3 of n, x4 of n, till all the samples get completed in x of n. And the size of each blocks x1 of n, x2 of n, x3 of n should be what? Capital L, right? And that L minus 1 number of zeros, for example, if L is equal to what? If L is equal to 3, then 3 minus 1 is what? 2. So 2 zeros you have to add to the h of n to make the length of h of n is equal to the size of DFT, right? So here you can observe, here you will understand clearly. So this is my input data sequence x of n, right? And we have to divide this input data sequence into a number of blocks. So x1 of n, x2 of n, x3 of n and x4 of en, right? So in this x1 of n, each block we have to make the length of each block should be equal to the size of DFT. So size of DFT, if I take n is equal to 5, and if x1 of n size is what? L, right? And n is equal to, we know that L is equal to n is equal to L plus m minus 1. So the length of this one is what? L. To make n, because n is equal to L plus m minus 1. So this is L, so this is L and this is m minus 1. If you add L plus m minus 1, you will get n, and this n is nothing but size of DFT. Similarly, and here one more important thing is, you have to add m minus 1 zeros at the beginning of each blocks, right? So this is my second block, x2 of n, and the length of this block should be also what? L plus m minus 1. So here we have L, m minus 1. So m minus 1 data should be 0, right? M minus 1 0, and here these m minus 1 should not be a 0. So these m minus 1 data should be from the previous block. So what is the previous block? This one. So m minus 1 samples you have to take from the previous block. For example, this x3 of n, you have to add m minus 1 number of samples from the previous data. Previous data is what? x2 of n. The last m minus 1 number of samples you have to add at the beginning of x3 of n. Similarly, from the last m minus 1 number of samples from the x3 of n, you have to add it to the x4 of n at the beginning. So this is how we segment or divide the long input data sequence into number of blocks, right? Only you have to add m minus 1 zeros for the first block, right? And for the second block, you have to consider, you have to take the last m minus 1 number of samples and you add it at the beginning to x2 of n. Similarly, last m minus 1 data to the x3 of n, last m minus 1 data of x3 of n to the x4 of n, right? And here, after performing the long data sequence into a number of blocks, next, and already you have added m minus 1 number of zeros. Now x1, if you see the length of x1 of n and h of n, both are same now. When the length of both the sequences are same, you can easily perform the circular convolution, right? You have different methods to perform the circular convolution, mathematical methods, right? Concentric circle method is there, then matrix method is there, right? Then table method is there, or one more method is frequency domain approach is there, right? So perform x1 of n circular convolution with h of n, you will get y1 of n. Second block x2 of n, perform circular convolution with the same impulse response h of n, you will get second output, second convolved output. Similarly, you perform the third, then you will get y1 of n, y2 of n, y3 of n and y4 of n. So like this you will get, right? And in the overlap save method, after performing, before you combine, you get combined output data sequence, you have to do some procedure here. So what procedure you have to do is, in the first output block, in the first convolved output block, you have to discard first m minus 1 samples. In the first block, you have to discard first m minus 1 block. In the second block also you have to discard first m minus 1 data. What is this m? M is nothing but what? It is the length of impulse response h of n. If the impulse response length is 3, then you have to discard m minus 3 minus 1, 2 samples of each block you have to discard. and here also you have to discard, and here also you have to discard from y4 of n, and finally you will get the output y of n, right? And here we will see one example. It is overlap save, examples on overlap save method. So the input sequence is given x of n, right? So we have we have a very few number of samples in x of n, but see the h of n, right? H of n is having very few samples, that is 1 1 1, right? The first step is what, right? So they will mention, so how many point DFT you have to perform to get the output of a system, that is LTI system. Otherwise you have to assume. So here n is equal to pi u is taken. So now you have to make, right? You have to determine the length of h of n. What is the length of h of n? That is capital M is equal to 3. So how many samples are there? 3, right? So how many samples you have to append to each block later after dividing? M minus 1 samples, that is M minus 1 is equal to 3 minus 1 is equal to 2. Next, now we have to divide this x of n into blocks, and here you have to determine how many number of samples I have to consider for each block. So that is given by what? N is equal to m plus m minus 1. So you have to calculate L. So L is equal to how much? 3. L is equal to 3. So each block should have L is equal to 3, right? So for example, right? So here you can see L is equal to 3. So I have taken 3 minus 1 0. 3 samples I have taken. Next, after 3, next 3 sample for x2 of n, 1 3 2. Next 0 1 2. Next is what? 1, right? So here I have taken 1. But to perform the circular convolution, your length of x1 of n, x2 of n as well as h of n should be same as that of size of DFT. Size of DFT is how much? 5. So now we have to make the length or size of these blocks equal to 5. So to make 5, how many number of zeros I have to add to the first block? M minus 1. So m is what? 3. 3 minus 1 is what? 2. So 2 zeros I have to add at the beginning of x of 1. Similarly for x2 of n, you should not add zeros here. Instead what you have to do is, you have to take the last m minus 1 samples of x1 of. What are the last m minus 1 number of samples of x1 of n? Minus 1 zeros. So these minus 1 zeros I have to add here, followed by next 3 samples from x1 x of n, 1 3 2. Next for x3 of n, the first 2 samples should be from the last 2 samples of x2 of n. 3 2 I have taken. Next remaining 3 samples should be the x of n. So that is 0 1 2. Next for x4 of n, so this division of the long data sequence is continued till the last samples of the x of n. So last sample is 1, right? Then you put remaining 2 samples 0 because I have to make it 3, and first 2 samples are from previous x3 of n. Next, you perform the convolution y1 of n is x1 of n into h of n, right? So we know that h of n, so h of n is nothing but 3. So to make pi u DFT size, I have to append or add how many number of zeros? L minus 1 number of zeros. So L is 3, 3 minus 1 is equal to 2. So after performing, you will get y1 of n, y2 of n, y3 of n, y4 of n. Now you have to combine to get the final result, right? So here this is y1 of n, y2 of n, y3 of n, y4 of n. Just recall the procedure, the theoretical procedure we discussed, right? So what you have to do is, so from each block, output block, you have to discard the first m minus 1 samples. M minus 1 is what? 2. So these discard, these are discarded, 3 2 2, 0 4 6, 5 3 3, and then 4 3 1, right? So this is how we perform the output of LTI system. We find the system response using overlap save method, right? So in the example, you will get a questions like this. They will give x of n as well as h of n. So you have to find the output response of the LTI system using overlap overlap save method. So for overlap save method procedure is different and overlap add method is procedure different. That